All right, it is time. Let's get started. This is a review day. Haven't they all been reviews lately? Yes, they have, but this is review for exam 4. Pulling in our focus, the last 3 days have been review for the whole final, for the whole course. This is just a review for exam 4, which is coming up on Wednesday. And this is just an old version of the exam. Questions are, worded different, structures are different, but the concepts are the same. The questions will be pretty similar. I'll give you just a minute to look through this one, then let's take your pick. Start taking your picks and go through it. I think I will suggest myself most of 14 and 15 we cover. Those are reactions. And it's just different versions of the same thing, same cast of characters of reactions, but the more you do that, the better. Here's a couple of copies.
Thank you.
Okay, maybe just another minute or two and then we'll get going. All right, taking questions here. Start with, I hope first of all that some of them look kind of familiar. They should look really familiar by Wednesday, but let's get a start on it here. Starting on that first page, does anything jump out at you? 2, okay. How about the next page? That one might be one of those that we do all of them, huh? Yeah. Okay. All right, I was expecting this to be kind of reaction heavy, and that's just fine. Okay, anything on that page? Just what, just 8 and 9?
Yeah.
Which one? 9, okay. 10 through 13 are short answers, naming, that kind of thing. Okay, Denny. 12. 13 it is. Oh, Brianna. Okay. Okay, then all of 14 and I think all of 15. The remaining questions are mechanisms. When we get time, I'll try to touch those pages, especially things be careful to not do. There are certain common mistakes at this point in the course. Okay, so let's see how many of these we can get through. The first one, number 2, if that will please focus. Which is the most stable radical? Well, what you're looking for is this kind of thing, tertiary being the most stable, and at the bottom of the list, methyl. Up at this end, you also have, not just tertiary, but also places where you have lots of resonance structures on the carbon with the radical. Okay, those belong up here. And it might just help to just walk through here. This one is probably the very least stable. That's methyl. It has no place to spread the pain. This one is primary. This one is secondary. This one's primary. This one's secondary. Now, you make that call by looking right at the carbon where the odd electron sits. Count the number of carbons bound to it. So it's 2, 1, 1, and 2. Well, it's sure not going to be any of these. You can knock those out right away. Of the two secondary ones, it looks like this one right here, first one, even though it's both secondary, this first one, which is B, has lots of resonance structures possible. So that's your reasoning. And you would say, well, it must be B then. Okay, moving on to the next ones. All right, so there's 3 different pathways that somebody's hoping to achieve. And it looks like the first 2 are just adding water. How about if we start out by tagging carbons? In the original alkene, it's those 2 right there. So you're looking at those 2, those 2, those 2. And there's going to be a way to make all of those things happen. So let's do a matchup now. This first one looks like it adds water. Okay, first one. Add water. And how can you tell that? Well, it's because compared to where you started, where you end up, one of those carbons picked up a hydrogen and the other one picked up an OH. Okay, everybody able to see that? Okay, so you're adding water, and are you adding it Markovnikov or anti? Yep. So there's what you're looking for with that addition. The hydrogen adds, the new hydrogen adds, where there already are the most. It's not too much of a stretch to look at this next one and say you're also adding water, but is that Markovnikov or anti? That one's backwards, yeah. Okay, now the last one isn't either one of those. It's not adding water, at least not by the time you're done. So let's come back to that. Okay, so this first one right here is an addition for adding water. And does anybody remember, is that adding it regular, no, Markovnikov, or is it adding it backwards? Markovnikov or anti? This one's Markovnikov. And the next one is just a way to reverse it. This one's anti. And then down at the bottom, those last 2 look like they're an attempt to put on OH in place of a bromine. Okay, so let's come back to them. We know that we can match A and B to one of these choices here. All right, transformation 1, that's this one right here, could be accomplished by reaction sequence. It looks like A. We're looking for Markovnikov. Transformation 2 could be accomplished how? Now this is an example of a question that's kind of intended to lead you to an answer, a little bit of a hint. This is telling you that sequence D ought to accomplish the same thing as the choice that you're making here. And we already know that transformation 2, looking like it's anti, that could for sure be done with B. All right, so look out. These two right here, both of those make an alcohol. So that's a little hint. So transformation 3, that's not adding water at all. Right there, you don't end up with an OH anywhere. So let's just write that little note about it. So this is not adding H2O. So you don't want to say A or B for that one. It's not A or B. Which one is it? Well, let's look at what's being proposed here. Both of these start out with HBr, but one of them has a big difference from the other one. It's got a little bit of peroxide thrown in, so that means that you know it's going to be backwards. This very first step right here is going to add HBr, Markovnikov, and the second one, just in the first step, will be anti-Markovnikov. So it's adding not H2O, it's adding HBr. Okay, that's where you'll be as at the end of the first step. And then along comes KOH. So I think what I'll do is sketch down here where we've got plenty of space. No, sorry, that's not what I wanted. Okay. So let's do these two steps. HBr. First of all, now here's a review chance in itself. The framework, carbon framework, keep it exactly the same. So as of the end of that first step there, there's what you have. Carbon's guaranteed there. And then the newcomer will be HBr with the hydrogen where there already were the most, so that's out at the end, which will be that right there. That's Markovnikov addition. Now, the way to make that backwards is the way it's listed in that last option, which would be D. So again, start out with your carbon framework exactly the same, except you put the bromine on the other spot, the other end of the alkene, which would be right there. Okay, now again, this is going to be C and D. And then the next step says KOH, which would be the same for both of them. Both those choices conclude the same way. So you come in with this choice on the first one. Let me do the last one. This one, remember, is primary as it's drawn, and this one is tertiary, the exact opposite. Really crowded versus not very crowded at all. Well, this looks like KOH, nucleophile, RX, that's a recipe for SN2. And so you have this as the final product, and keep your carbon framework the same. OH will replace the leaving group. You got an alcohol. Well, that's sure not what transformation 3 is. Transformation 3 is looking for an alkene. In other words, that's an elimination, which this is. Remember, what really sets this apart is this combination of two things. Tertiary RX and the other reaction partner being a strong base. That's your recipe for E2. And it would want to eliminate so that you wound up with the most stable alkene in the world that you could get out of this. And it would be this. Okay, that looks like, let's get back to the choices here. Transformation 3 could be accomplished by, that would be C. And there's a radical in the mechanism of reaction sequence D. this is caused by, that's always your clue, so you'll see that second semester, your peroxide. I don't know that it was planned to make the answers in order A, B, C, D, but that's the way it worked out. Okay, there's several things all teased together there. That's material from 2 different exams mixed together. It's all part of the same stuff. Okay, yeah. Oh, okay. Okay, any questions on that? Okay, let's do this one here and then start more reactions. 2 compounds shown at the right. I don't have any at the right. Do you?
No.
I don't know. Somehow that copy didn't get them. Sorry. Need to skip that one. Okay, let's skip this page with 10 to 13 on it. Come back to it if at all possible, if we got time, and in the meantime, try to knock out some of these things here. Okay, now this is stringing together, each one of these is stringing together 3 steps. So that could all be from the alkenes chapter, or it could kind of cross between chapters. And let's just work through this. The first one is from your alkynes chapter. Let me write something as the final product of each one of these steps. Let's see if I got enough room here. Okay, alkyne plus an extremely strong base. Well, I hope that started to kind of sink into your memory from this chapter we just finished up with alkynes. The only thing that happens is you wind up turning that alkyne into an anion. So I've got this as an ion. Now sodium is the countercation. There's another product, NH3, that you can ignore. That's not the organic product. So remember that this is now going to be a good nucleophile, and you are giving it something that it would like to displace. This is now Rx. And so your next product is going to be the X knocked out of this piece here and replaced with the nucleophile. Now you can draw it either way you want, right to left or left to right. I guess I'll go with the ring first. So here's the triple bond, still very much intact, and here it is now bound to the other piece of Rx. So there's R. Let's just kind of tag that. Here's R, and this much here, that's R. Nucleophile came in and knocked out the leaving group. Okay, now the story right here, let's put this in words instead of trying to draw a whole bunch of structures next to it. What does this do? Well, I hope you're starting to recognize it, is it reduces an alkyne, but very carefully and very selectively. It's not like throw on all the hydrogen you possibly can or put it in any possible spot. It reduces it to the trans alkene. Okay, well, it'd usually be easiest to draw the alkene somewhere in the middle of your final product and say, well, whatever happens, I need to make sure that I have my main chain going in on one side and coming out on the other. And I suppose I'd start into it, get a good strong start like that. And what have we got here? So this one carbon has the ring as its other partner. So there it is. And then the other carbon has the R group. What's that? 3 carbons? 3 carbons in a row. So that is drawn to look like it's trans. And to emphasize that, since we're drawing the structure fully out, the hydrogen should also agree. Definitely should be clearly trans. Okay, a little pause there. Just kind of follow all those. I understand it's a lot easier if somebody's doing it for you and talking about it and so forth, but Is there anything you'd have trouble catching if you came back to it? Okay, Brianna.
Oh, the first step, I don't really understand like what you did right there.
Okay, see this hydrogen right here? That's pulled off. I'll just stop and not clutter it. It's pulled off by the NH2 minus, which is a really strong base. And that leaves you now with this thing. It's an anion. It's the whole alkyne to begin with, except the hydrogen. You can now turn it from something that's this nice, neutral, no charge, innocent thing into an aggressive anion. That makes it a nucleophile that can go and attack this piece. One hydrogen, that makes the whole difference. Okay, any more questions there? Okay, so let's tackle this next one. Now it starts off in kind of a familiar way. So let's say, it's the fact that it's lithium other than sodium, not a nickel for the difference. You've got an extremely strong base, and so now you have H, and the other end, it doesn't matter which one you choose, but just make sure that you've converted this into an anion. So that's your nucleophile in the next step, with this time lithium as the counter cation. Okay, this now again is a nucleophile, and again you're going to feed it an Rx. Well, R this time isn't a little 3-carbon piece, it's a ring plus another carbon in the middle. So I suppose we better keep track of it like this. And yeah, I'll go ahead and start this carbon-carbon triple bond. And it has on it now, I'll draw this out. Okay, now what you don't want to do is forget that CH2 right there. Okay, maybe you don't need that little extra added note, but you don't want to forget it, such that when you come over here to draw the product, you're missing a carbon. So here it is, and this stage right here, this is going to add water, and it adds it specifically, anybody remember, Markovnikov or anti? Well, here's the way you remember. The minute you see a borane involved, you know that adds first, and so it's going to be anti. Okay, well let's first of all get the carbon framework right. We know we're guaranteed to have a hydrogen, and we're going to have a carbon with at least one bond to its neighbor, and then we're going to have the rest of the molecule which does nothing. Okay, now I'm going to leave that all in one color just to kind of show that that's where it happens. All right, now what you want to do is be looking here back at the compound that you added water to in the final step. The one on the left, that one has more hydrogens, and of the two, the other one has fewer hydrogens. So you're looking and you're saying, well, if this were Markovnikov, the new hydrogen would go out here. But it doesn't go here. It goes to this one, meaning that the oxygen is going to go to the terminal carbon. Now, if you want to just draw that much, you're okay. What you don't want to do is draw an OH there and stop, because what we know is it doesn't stop there. It goes to that point, and both the new hydrogens, I said I was going to use a different color, both the new hydrogens go onto the other carbon. Okay, let me add just one, I hope, note without cluttering it too much. The new hydrogens went here. That's backwards. If this had been Markovnikov, they would have all crowded onto the very end where there was more to start with. There's your final product. Again, that's pulling together several things. Okay, then the last one, we'll take a step back and see what questions there are on the page. Okay, the next one starts off pretty straightforward. Adding HCl to this alkene, totally Markovnikov. There's no water around, nothing special at all. Okay, again, start by drawing your carbon framework and getting it right. So there are 6 carbons tied up in the ring, and there are 2 that are not in the ring. Now we'll come back and fix that, but let's at least get that much right. HCl, well, let's see, it looks like it's adding to a situation where that one right there, again, if you're tracking, this one has more hydrogens, and so it ought to have more hydrogens at the finish, meaning that the chlorine will be on the other one, which would make that product right there. It adds to the carbon that's already part of the ring. Okay, now look out. What you've made here is a tertiary RX, and you are next confronting it with strong base, which is a recipe for, and they all said, E2, the most missed question in the course. It's so tempting to want to take that OH and put it in the chlorine. You know about substitutions, they're convenient, they're straightforward, but not that combination. Nature doesn't always make it that easy. All right, then you just say what would be the most stable product to come out of an E2 reaction. Now again, get your carbons all in place. 6 in the ring, 2 out. Well, that chlorine could easily eliminate with the hydrogen that's next door to it. You just made an alkene, as will always be the case in an E2 reaction. The final one ought to be one of the easiest in the course. You're going to add H2. It's not even tagged up with something fancy like deuterium. It's just slap on hydrogens. Okay. It would look like that. Now, technically, I guess you could say, let me do it this way. The stereochemistry is known. Methyl groups would both be up, and the hydrogens would both be down. You wouldn't have to draw those hydrogens. Okay, add hydrogen, and as you do it, they're both adding definitely cis. Okay, there's a page of, pretty demanding pulling it all together in one string after another. But what one thing jumps out at you? I'm going to cover any one thing here. Okay, John. This one right here? Okay, Jillian's question is about this one. It sure doesn't look like it's water. All right, but the recipe in here after sodium borohydrate actually includes a little bit of water, but that's not how the water comes on. The first hydrogen, as in H2O, actually comes from that thing right there. It's not even water adding in the first step. You're getting your hydrogen from a different source, and I'm glad you asked that because that's also true back in the alkenes chapter. Remember it had BH3? Well, that's part of the story of adding water, but it starts out its life on boron, not water. So this is really a way to add water. And like Jalen pointed out, it sure didn't look like there's any water in there, but it's a special set of steps that were developed that accomplish just that. Okay, more questions? Yeah, please. This one right here? Okay. It adds cis, hydrogen adds cis, because the catalyst is going to be a flat surface. The metal in this case is platinum. But if both hydrogens go on, and this may be your real question, if both hydrogens go on from the same side, then they're both pointed the same direction, which also means that, this is what we started with, both of the hydrogens are down, then both of the methyl groups also have to be pointed in the same direction. That make any sense there? Let me redraw this. If I had simplified this and drawn it as this, would that kind of see that? Alkene, alkane. Adding hydrogen. In fact, let me pull this piece up here. Okay, there's literally what we're talking about. Platinum and hydrogen. Going from here to here, and since we don't really draw hydrogens, it would be partly accurate to draw this. Now, I wouldn't show stereochemistry. So, you okay with that one?
I guess I'm asking where the hydrogens at.
Where are they at? There's one hydrogen goes here, and one here. So to begin with, on that carbon, you got no hydrogens. When you come here, you got one. So there's one of them. And on this one, no hydrogens. On this one, you got one.
So they both attack from the backside.
They both what?
Attack from the backside.
They do.
That's why it's
That's why it's cis. They come in, the hydrogen is actually bound to the metal, like this tabletop, and here comes the alkene, like that. Okay, any further questions? Now the good news about this page is that it'll make this one kind of easy. In fact, hint, there will sometimes be answers kind of built into your simpler ones that might help for the longer ones. So let's kind of run through this. Okay, first one is an alkyne. Adding 2 HCl's. There's nothing strange about the orientation here. As always, get your carbon framework right. And I'm going to draw this end of it kind of big. The ring does nothing. And there are only 2 carbons other than the ring, both of them alkynes. Okay, so the new hydrogens we'll add here. And the 2 chlorines will have to be in the other spot. And you're done as of that spot. Now, what you might want to remember is you had originally 1 hydrogen here, and now you've got 2 new hydrogens. There they are in that carbon. It's awfully easy to forget to draw a carbon unless you start by, drawing the carbon framework. Get it nailed down. Okay, the next one tells us to start with an alkene and add something to it. It sure looks like the site of the action was that right there. And there's several things that looks like they could have come and sat on an alkene to get there, but I would hope that the main thing that would stand out to you is these 2 chlorines right here and the fact that they are trans to each other. One's up and one of them's down, which sure sounds an awful lot like you added to an alkene just Cl2. These lunken big halogens, they add to an alkene, so one's up, one's down. All right, go back, get the carbons in place. And it looks like there's 6 in the ring and there's 1 off the ring. So I'll go ahead and draw it as a methyl just to be sure. And those 2 carbons that are tagged red in the final product, that must have been the spot where there was, and here is the change. That's where the alkene must have been. Okay, sometimes I'll see answers where the student has done a really good job of figuring out what combined, The halogen must have come here, must have come to these two carbons, but we're missing the double bond. That's what makes the whole thing possible. Okay, next one. We're given an alkene, and let's just figure out what it is, the route to get us to the point where water is added. How did water add? Well, you have two carbons to choose from, and it looks like the first one, that one has the more hydrogens, and the second one there in the corner got none. All right, and then again tracking carbons, those two right there. It sure looks like the new hydrogen added here, OH is on the other spot. The new hydrogen added where there were not most to start with, right? So is that Markovnikov or anti? Yeah, okay, so it added anti. And your recipe for that starts off with what you always start off with if you're wanting to add water backwards, some borane. And then in the final step, there'd be it's peroxide, mild oxidizing agent. And it's usually done in base, so you don't tear up the molecule. Okay, borane followed by an oxidation. Okay, the next one is pretty straightforward. You're given your starting compound, the alkene, plus a reagent, and here's what you want to remember. This is going to add 2OH, and it's going to add them both on the same side because you got this big old metal that delivers it. You want to allow plenty of room for the space between those two carbons. So get the ring right. It's 5, and we are now tracking those two carbons. They're kind of drawn on the right hand side. Okay, now you're going to need to draw, I'll draw them both down just to make it easy to see. Your OHs are both going to be on the same side, so cis. And there's one other carbon that's not accounted for until you finish it up by drawing it in that spot right there. Okay, if two OHs are on one side, that means the starting methyl must be on the other side, whatever it is, pointing the opposite direction. Okay, this next one right here, this is a little recipe for, again, breaking up alkene double bond and adding something on either side of it. That's the scheme of all the alkene reactions we had. But this is going to be something different in the sense that what it adds is a little bridge between the two sides. So that pi bond will go away. And okay, let's get the carbons where they belong. And I'll draw kind of a big space. There's all the original carbons right there. The alkene is those two. And then the piece that comes in is CH2. Now, try to keep your drawings as consistent as possible. So there's no need to go drawing in a letter C and 2 hydrogens because you can account for that in the drawing. That's the new CH2. Okay, it's got a hand reached out in either direction, and it bridges the original alkene carbons. Okay, this next one looks like again you have something that's bridging 2 carbons, and one reaction you do know that we've been through that accomplishes that starts with an alkene, and in fact here's kind of your guidance. What alkene would I start with that looks like it has the potential to wind up looking like that. Well, the two carbons where the action has taken place, that ought to be where your alkene gets drawn. And again, get that alkene there. Get your right functional group. Okay, does anybody remember the reaction it took to get that in place? Okay. If you remember that much, we'll call it good. Okay, so the next one is a polymer question. And you can tell that it is polymer because you got this number here. It's a big number. We don't necessarily know how big it is, but we do recognize it as a polymer by that big number. And, okay, again, you back up to an alkene, recognizing that you must have put together a bunch of little things, that many little things, to make something as the final product that was that big. Okay, carbon framework, again, get that. And the challenge, if there is one here, I guess, is recognizing that there may be a difference between the two carbons. I'm going to just number them 1 and 2. Don't usually do that. Number 1 has on it a hydrogen and a chlorine. There's the chlorine. There's the hydrogen. And number 2, well, they're both the same, methyl groups. And then maybe the single most important thing, get your alkene double bond in place. Okay, now this next one actually includes a reducing agent after the ozone. Actually, I'm thinking of a better answer to number F. Do you remember this little abbreviation here? Monochloroperoxybenzoic acid. That's your most specific answer. O3 by itself, yeah, we kind of accomplished this, but let's get it down to this stage right here, because this combination has an overall effect, which is that it splits the original alkene in half. Now, it's still breaking the pi bond. That's the whole theme of the alkenes chapter. Break that alkene. But it doesn't stop there. It goes one more step. And the way you track this is go straight for your alkene and say, well, there's the first spot. Those two right there. There's the first spot that had an alkene in it. So that carbon right there, when we're all done, will be bound to a new partner, an oxygen. Don't forget your hydrogen, which was there to begin with. The other piece of it, it's probably easiest to remember if you keep these things kind of lined up the way they were. There's the other piece, just 3 carbons. And here's the oxygen to it. Now, there's an alkene carbon. There's an alkene carbon. You just took the whole thing and neatly split it in half with an oxygen on each side. Okay, I think we've got time for this last one. So here's a 3-step one, kind of sneaked in on you. And how about if we say, well, what have we got as of the end of the first step? We have a secondary Rx at an extremely strong base. That's a recipe for E2, meaning that as of that spot right there, you don't have to draw this if you don't want to. In your final answer, we're just going for what's in the box, but your final answer should look like this. You'll have the methyl group still there, and the most stable alkene you could think of the options would be that one right there. So there's E2, made its elimination product, an alkene, exactly like it should. Okay, then these last two, let's remember what they accomplish. This is a recipe for adding not water, HOH, it's adding HOR. So just one thing different from water. One hydrogen gone, one R group in its place. And it does it Markovnikov. Now there's a little story on that. So let's come over here to the final structure. Allow some room towards the bottom for the final answer. Okay, there's the original carbon set. So you've got two rings joined on an edge, and that one methyl group dangling off there that does nothing the whole time. It's just there. And you had this alkene, which, to begin with, you can tell the two sides apart. There's one hydrogen there. So compared to the other one, that's more. And the new hydrogen should add to that spot. And the new R group is this piece right here. Okay, that's OR. And to that carbon right there, you have hydrogen having added. It's not shown separately as hydrogen. Okay, we managed to get through the reaction intensive part. If there are specific questions on any of those, I'll go back and hit them. Otherwise, just a quick few heads up on the mechanisms. Questions? Okay, Brianna. On this page?
Yeah. Actually, that's fine.
Okay. Okay, let me see if I can say something about the most common problems here. Okay, this one right here. And this one, remember, HOH. That's the first thing that reacts with your alkene. Nothing else jumps out at me there, I guess. Okay, and this one, H plus from HBr, that's first. Usually if you can get off to a start like that, those will go okay, or at least better than otherwise. Okay, in this next one, there's a little theme to these two. Both of them involve radicals. Now the thing about radicals is, and this may seem picky, but it'll help you keep track of where you are if you remember. Arrows are single barbed. So, like that. I know that looks picky, but it sure does tell a different story. It'll help you remember that you're taking one bond, one pair of electrons, and splitting it in half, one going each direction. Okay, I think the rest of it is probably not worth our time here. All right, we may not have gotten to all of it, but I hope that's the hardest part and the most of it. Okay, better quit there, and the keys to all the quizzes are now open on D2L. Please look back at your quizzes, review those, check what you got, what you didn't. I'll see you Wednesday.
I'm sorry to ask. Can we also get keys to the questions that we didn't do?